Why does the electricity in your home keep changing direction 50 to 60 times every second? Why do some circuits behave calmly while others suddenly explode into huge currents? And why do coils and capacitors fight against AC even when they allow DC easily? All of that comes from alternating current. Take a small coin and slide it back and forth on a table. Left, right, left, right. It never settles in one direction. It keeps switching. That's exactly what AC does inside your wires. In AC, electrons don't travel from the power plant to your house. They simply vibrate back and forth, pushed first one way, then the other. This switch happens 50 to 60 times per second, depending on your country. That vibration, not forward motion, delivers energy across long distances. This is the learning studio, turning complicated electrical ideas into clean, simple logic. In DC, the current flows one way. In AC, the current reverses direction repeatedly. And when current keeps changing, the components inside the circuit behave very differently. A resistor behaves normally. It opposes both AC and DC the same way. But a capacitor resists current more at low frequencies and less at high frequencies. Fast changes suit capacitors. They can charge and discharge quickly. Slow changes frustrate them. An inductor is the opposite. It resists current more at high frequencies and less at low frequencies. Inductors hate quick changes. They fight them with their magnetic fields. Together, resistors R, inductors L, and capacitors C create RLC circuits, the backbone of radios, filters, speakers, and power systems. In AC circuits, the total opposition to current isn't called resistance. It's called impedance, because it includes resistance plus capacitor behavior plus inductor behavior. Impedance changes with frequency, which is why some frequencies pass through a circuit easily while others are blocked. And here's the most beautiful part: resonance. If the frequency of AC perfectly matches the natural frequency of an RLC circuit, something magical happens. The capacitor and inductor cancel each other's effects. The circuit suddenly allows huge current to flow with almost no opposition. That sweet spot is resonance, used in radio tuning, antennas, sound systems, MRI machines, and even in wireless charging. AC is everywhere because it can be transformed to high voltage for long-distance transmission, then safely stepped down for homes. It powers industries, buildings, hospitals, everything. Now think about this. If alternating current constantly creates changing magnetic fields, what happens when those fields leave the wire entirely and spread through space? That leads directly to electromagnetic waves, the wireless world we live in.